Splitting of d orbital in tetrahedral complexes is, in case of tetrahedral complexes, d orbitals do not split. It is the reverse of the octahedral complex, same as an octahedral complex and none of this. So if you see octahedral complexes and the tetrahedral complexes, in case of octahedral complexes, the ligands approach along the axis, whereas in case of tetrahedral complexes, the ligands approach in between the axis. And if you have 5 degenerate d orbitals, we make 5 boxes for d, and those are dxy, dyz, dzx, and dx square minus y square and dz square. These orbitals have their lobes in between the axis, and these have their lobes along the axis. And in case of octahedral complexes, since the ligands are approaching along the axis, the orbitals which have their lobes along the axis, due to the repulsion between the electrons of the metal and the ligand, there will be more repulsion and their energy increases. So these were the orbitals along the axis, and these were the orbitals having their lobes in between the axis. So this would be the crystal field splitting. And in case of tetrahedral complexes, the orbitals which have their lobe in between the axis, since the ligands are coming in between the axis, their energy increases, and the orbitals having their lobes along the axis, their energy decreases. So this is the type of splitting. If you observe these two types of splitting, it is the reverse, where you can see this particular thing that's called as EG and T2G level here, but here the T2 goes up and E comes down. So the answer would be reverse of octahedral complexes. The octahedral splitting is seen in tetrahedral complexes.